Welcome to the deep dive. Okay, today we're jumping right into something pretty intense, what people are calling the quantum architecture wars.
Mm.
Forget the noise about qubit counts for a second. This is about the fundamental blueprints, a real fight for dominance in quantum computing happening right now.
Yeah, it really feels like the 1980s computer battles all over again. Amiga versus Atari ST, maybe. But the stakes here are just way higher. We're asking which basic design philosophy actually survives the jump from, let's say, lab experiments to genuinely fault-tolerant machines.
Okay, let's make that analogy concrete for everyone listening. We've got two totally different ways of building these machines.
Yeah.
So who are the main players here?
Well, you've got the Amiga camp, that's the nearest neighbor, or NN approach. Think superconducting qubits, IBM, Google. Their idea is basically leverage what we know from making classical chips, fixed 2D grids, lithographic stamping. It's rigid, yeah, but the hope was faster scaling, initially at least.
Okay, the pragmatic approach and the Atari, the sort of high-end custom build.
That's the fully connected, or FC, camp. Trapped ions. Quantinuum, ion Q. This is more. Physics first. It's way harder on the engineering side. You're controlling individual atoms in 3D. It's complex. But the payoff. Huge flexibility, massive connectivity.
And there's a third player too, right? The one kind of ignoring the hardware fight.
But hey, Acorn.
Acorn Archimedes.
Yeah, the Acorn, that's high-performance simulation. Things like PyCrack. They're just focused on solving problems now, especially optimization stuff, using really smart classical software, and honestly, they're winning certain races already while the others build the quantum hardware.
So for anyone trying to get up to speed, the real core of this hardware battle, the thing to watch, is connectivity. Our sources say it may be as important as clock speed and gate fidelity because, connectivity shapes what algorithms you can even run and, crucially, whether fault tolerance is even economically possible.
And it's fascinating, right, how these two hardware camps looked at connectivity right from the start. They basically made a huge engineering bet.
A bet that gets described as trivial versus non-trivial. What does that actually mean in terms of the hardware choices?
So the NN side, IBM primarily, argued that making a 2D grid where qubits only talk to their neighbors. That's trivial from a manufacturing perspective. You use existing chip-making techniques. It keeps the initial engineering simpler, maybe helps avoid some physical errors like crosstalk early on.
Right, so NN consciously chose that simpler manufacturing path, get something built quickly.
Exactly. But, and this is the crucial but, they essentially deferred the whole connectivity problem, shoved it onto the software layer, the algorithms. That creates this massive connectivity tax that we really need to dig into later.
Okay, so if NN went for simple hardware now, complex software later, what was the non-trivial, the really hard challenge the FC camp took on immediately?
The FC side, Quantinuum for instance, they absolutely chose the harder path first. Getting true all-to-all connection with trapped ions, it's a huge engineering lift. Non-trivial is an understatement. You're literally shuttling individual atoms through these complex 3D traps, guiding them to interact. Think nanoscale billiard balls.
Wow, so they accepted that immense hardware difficulty right away. For what payoff?
Zero future software overhead for connectivity. The hardware just does it. Any qubit can talk to any other qubit directly. Total flexibility. It was a massive wager on getting the architecture perfect from the start. And understanding that wager helps explain why we're seeing performance gaps opening up now.
Let's look at the consequences of that NN bet then. Starting with superconducting systems, IBM's heavy hex design. It seems almost defensive.
It is defensive, and this is so important. Heavy hex actually reduced the connectivity compared to some earlier IBM designs. Think about that. Everyone wants more connections, and they deliberately chose fewer. Why?
Yeah, that sounds totally backward. Why cut connections when it's the key metric?
Because of the messy physics you get when you cram superconducting qubits too close together on a 2D chip, they ran smack into problems like frequency collisions, qubits accidentally affecting their neighbors, what they call spectator qubit errors, or crosstalk. Heavy hex was designed specifically to create space and reduce those physical errors.
So heavy hex reducing connectivity to improve fidelity. What's the hidden message there? What trade-off did IBM implicitly make?
The admission is basically that for current superconducting tech, you can't have both high fidelity and high connectivity easily. They're in tension. IBM chose fidelity first, which means the massive job of creating logical connections falls entirely onto the software, the compiler. They traded algorithmic power down the line for cleaner operation now.
Okay, that's a risky trade. But Google's Sycamore, in its initial form at least, had an even bigger limitation. Something about only having terminal measurement, lacking mid-circuit measurement, MCM.
Yeah, and that's, well, it's a fundamental architectural flaw, frankly. MCM lets you measure a qubit during a computation and then continue based on the result. Sounds technical, but its absence, it dictates their entire future path, especially for fault tolerance.
Maybe unpack that for listeners who aren't deep in the weeds. Why is having MCM or not having it such a critical fork in the road?
Okay, so true fault tolerance, the ultimate goal, relies completely on something called quantum error correction, or QEC. Active QEC needs constant checks. You need to measure HELPA qubits and SILAs in the middle of the calculation, see if an error happened, and then potentially fix it, all while the main computation keeps going.
And because Sycamore couldn't physically do that mid-circuit check?
Correct. It physically couldn't run those essential QEC stabilizer checks. So unless they completely overhaul the hardware, it's basically stuck being a nice Q-only machine noisy intermediate scale quantum. Bad connectivity is one problem, but being structurally blocked from the path to fault tolerance, that's arguably much worse.
Okay, let's contrast that with the FC camp. Mobility is key there. Tell us about Quantinuum's QCCD architecture, quantum CCD.
Right, QCCD. Here, the qubits aren't fixed dots on silicon. They're individual barium ions, atoms floating in a vacuum trap. Connectivity happens because they can move. You physically transport any two ions you want to interact from a storage area to a special gating zone, zap them with lasers to entangle them, then move them back or elsewhere. Computation becomes dynamic.
The big challenge for ion traps used to be scaling, right? Getting beyond just a single line of ions. How did they crack the 2D scaling nut?
The big innovation was the junction. Quantinuum really pushed this. It's essentially a tiny, ultra-precise crossroads for ions. It lets them route ions in 2 dimensions, building up these complex chip layouts. Think of it like a city grid for atoms. IonQ is taking a slightly different route, aiming to link separate, smaller, fully connected modules together using light photonic coupling. But both approaches break free of those fixed 2D limits the NN guys face.
And the advantages of FCC go beyond just moving qubits around, don't they?
Oh, absolutely. First off, trapped ions are perfectly identical. Every barium ion qubit is fundamentally the same as every other one by nature. Compare that to superconducting qubits. They're manufactured, so they have tiny imperfections differences. They need constant complex calibration just to keep them matched. It's a huge overhead.
And then you get the real killer combination, FC plus native MCM.
Yes. Native mid-circuit measurement and the ability to reset qubits quickly unlocks what we call dynamic circuits. This means you can measure a qubit, get the result, reset it, and reuse it almost instantly, all within one run of your algorithm. The efficiency gains are staggering. We've seen actual examples where, like, an 80-qubit optimization circuit QA-way was successfully compressed and run on just 20 physical qubits. That's only possible because of qubit reuse via MCM.
That's not just a small improvement. That's a different class of capability altogether. So the FC systems have the qubit mobility and the MCM capability, and that lets them run algorithms that are, as our sources put it, functionally impossible on hardware missing that combination.
Which brings us right back to quantifying the cost for the other side. That 3-part connectivity tax the NN architectures pay for choosing simpler hardware up front.
Okay, tax number 1, the most obvious one. The algorithmic tax, having to use swap gates.
Right. If your algorithm needs 2 qubits that aren't neighbors on an NN chip to interact, you're stuck. The compiler has to insert a whole chain of swap operations, basically, painstakingly moving the quantum state of one qubit across the grid, step by step, swapping it with neighbors until it reaches the target. This chain, this swap network, adds dollars. It gets longer the farther you need to go, and every single swap adds noise and potential errors.
Can we actually put a number on how bad that swap tax is?
We can. There was research looking at compilers designed specifically to minimize these swaps by being smarter about qubit placement. What they found was, just by optimizing the mapping to avoid swaps, they saw an average 138% increase in the probability of the circuit succeeding. That huge jump tells you just how much damage those swaps are doing in standard compilation. It's a massive, immediate penalty. And the FEC systems, they pay 0 tax here. Their connections are direct.
Wow, 138%, okay? Tax number 2 is the capability tax. This relates back to Google and MCM.
Exactly. It's not just inefficiency, it's a hard block for hardware lacking MCM. It means you simply cannot run whole classes of modern, powerful algorithms things using dynamic circuits, adaptive methods where the algorithm changes based on intermediate results. You lose the efficiency of qubit reuse, and as we said, you can't even attempt active error correction properly.
And then tax 3, The strategic tax, this is a big one for the future, right? The one that likely decides the whole war, tied to error correction and scaling.
This is where that initial 2D grid choice really comes back to haunt the NN camp. Their planar layout pretty much locks them into using 2D error correction codes, primarily the surface code. Now, surface codes are well understood. People know how to work with them, but they are incredibly resource intensive. The overhead, the number of physical qubits you need for each useful logical qubit is really high. They just consume physical qubits like crazy.
And the FTC architecture unlocks a different, much more efficient path.
Precisely. Because FC machines can connect qubits non-locally across distance, they can implement more advanced three-dimensional error correction codes, specifically quantum low-density parity check codes, or LDPC codes. And here's the killer number, the potential checkmate. Recent research shows a new LDPC code can achieve the same level of error protection as a standard distance DAS7 surface code, but using 4 times fewer physical qubits per logical qubit.
4 times fewer. Okay, that's not just a small edge. That's potentially game over territory strategically.
It's the existential threat to the NN approach.
Yeah.
Your NN machine has to be 4 times bigger, likely 4 times more complex, probably 4 times more expensive, just to reach the same level of fault tolerance as the FSC machine. You look at IBM's roadmap for 2025 to 2029, Nighthawk, Loon couplers, Starlink long-range connections. It's basically a multi-year, incredibly complex effort to retrofit long-range connectivity onto an architecture that wasn't designed for it. They're trying to engineer away that 4x deficit after the fact.
While this hardware war is raging, let's swing back to that third player, the Acorn high-performance classical simulation. How are they staying so competitive?
Yeah, you really can't ignore them. The PyCrack system is a great example. It's clever because it doesn't just rely on one simulation method. For really complex, highly entangled circuits, sure, it hits the same wall everyone else does classically, maybe 30, 40, 52 bits max using standard state vector simulation.
But it can simulate hundreds of thousands of qubits sometimes.
Yeah.
How?
That's its other engine, the QBDD engine. It uses special compressed data structures. If the quantum circuit has some underlying structure, if it's not maximally entangled everywhere, which many useful circuits aren't, QBDD can exploit that structure. It compresses the representation, allowing simulation to scale way, way further for those types of problems. But the real weapon, commercially, that's the separate PyCrack-izing library.
The Acorn CTU, what makes that specific library so potent?
It's laser-focused. It's not trying to simulate any quantum circuit. It's a highly optimized classical heuristic solver built specifically for classical optimization problems formulated in a certain way, QBBOs, traveling salesmen, things like that. It uses quantum-inspired ideas but runs entirely on classical hardware, tailored for this very lucrative market segment.
And the performance in that segment is sobering for the quantum hardware folks.
Definitely. It's already tackling optimization problems with tens of thousands of variables. That scale is just completely out of reach for any current quantum computer, whether it's NN or FC. We even saw that paper in 2024, right? IBM and IonQ researchers collaborated, used a classical algorithm, and it just blew away a recent quantum experiment result, solved it better in milliseconds.
So it's a two-front war for quantum hardware. You have to beat your quantum rivals, and you have to beat the best classical simulators and solvers on their home turf, especially for optimization. The Acorn is leading that race right now.
So let's pull it together, the NN approach. Pragmatic start, easier manufacturing, yes, but it baked in this huge compounding connectivity tax. Poor algorithmic performance now, potentially fatal QEC overhead later, the FCC approach. Much harder engineering upfront, absolutely. But it built in the necessary features, full connectivity, MCM from the start. That gives it a potentially much cheaper, more direct path to fault tolerance using things like LDPC code.
And thinking about that tax, there's this weird lag effect happening now, isn't there? Even with new FC machines available, a lot of the software and algorithms still feel like they were designed for NN limits.
That's exactly right. Because NN systems dominated cloud access for years. The whole ecosystem, researchers, textbooks, software tools, compilers, got trained on thinking within NN constraints. We have this kind of algorithmic inertia or mismatch. Powerful FC hardware is here, but people are often still running algorithms designed with limited local connectivity in mind. We haven't fully unleashed the native capabilities of FC yet.
Which really brings us to the final thought, something for you, the listener, to chew on. The FC architecture enables types of computation, dynamic algorithms, efficient error correction that are fundamentally functionally impossible on fixed grid NN systems lacking MCM. So the big question is, what completely new class of FC native algorithms is waiting to be discovered now that those architectural chains of just talking to your neighbors have finally been broken? What comes next?